Welcome back, everyone. It's now time to start the final session for today, entitled Corrosion Assessment and Management. This session is chaired by Dr. Cheng, who is a professor and Canada Research Chair in Pipeline Engineering at the University of Calgary. With over 235 journal papers published, his research focuses on pipeline corrosion and integrity management, including external and internal corrosion of pipelines, microbial corrosion, erosion corrosion, stress corrosion cracking, hydrogen-induced cracking, defect assessment, corrosion modeling, and microelectrochemical measurements. Thank you, Dr. Cheng, for chairing this session, and the floor is yours.
Thank you very much. That's a very good opportunity to include my section in the conference. Also, I want to thank you everyone go to the last section of today's conference. That's a corrosion assessment and management. So we have 5 reputed researchers in this section, and they will present very interesting R&D research results. So our first speaker is Professor Chaofang Dann. Dr. Dann is with the University of Science and Technology, Beijing. She has performed excellent research in corrosion modeling and assessment based on the integrity computation. So next, we give the time to Dr. Dann.
Thank you. Thank you for the chairs and hello everyone. Today I will give a talk on the development, validity, and application of the integrated computational corrosion. I belong to the National Material Corrosion and Protection Data Center. And also we have an advanced innovation center in our university. So maybe next time, welcome all the friends come to our university to visit our center. And today I will show 4 parts about my presentation. And the first is a background. And as you know, all our corrosion exposure test, we need to do outdoor exposure. So most of the tasks on our National Material Corrosion and Protection Data Center provide comprehensive experts and service in the field of corrosion and corrosion control. So we collect and accumulate all the data from different atmosphere and also the seawater, the different soil conditions. So you can see we also get different environmental monitoring, failure analysis, and also material and equipment life assessment. So that's why I hope everyone in this part can visit our website and can give a small data for this part. And most of we do the outdoor exposure, so you can see the specimen for the atmospheric corrosion test, and we also use different kind of the samples to do some accelerated corrosion test with the laboratory. That is the background, but within recent 10 years, we know there are various types of the corrosion. So the reaction process may cover different scale, including the length scale and also some time scale. So we need to take our focus out not only about the corrosion experimental data, but also we need to use more modern method or some other technique to improve our study. So that's why I, based on the requirement and also based on the multi-scale, the challenge, I think we need to lead our group focus about the integrated computational corrosion. So that's why I use about 10 years focus on this area. So the key issues about we need to know is to exchange, integrate, and evaluate of the correlation and validity between the experimental and the computational data is very, very important. So in the past 30 years, we also search for different kind of the papers. We read a lot of reference, but we noticed that many papers just mentioned about the corrosion, the calculation, simulation, or some computing method, but more than 6,000 of the papers gave the calculation method in detail. So you can see we just use the software to do a statistic to analyze different kind of the method. From this figure, you can see the increasing papers number is very, very clearly. So that's why we choose this method. And another background is about from the physics or some chemistry field, we want to just use some new method to do our study. And that's why we just try to do a knowledge map of the mechanism acting and different simulation method. And from this map, we can see some hot point issue of the corrosion. The red one is about the corrosion inhibitor, and also the green one is focused on the oxidation, and others, the blue one is about the atmospheric corrosion, and other also about the electrochemical impedance. So that's from the knowledge map, we can know the relations, and also we can, for us, it's easy to get which area is very, very hot topic. So with recent years, everyone know in the US, it's in the material science and engineering about the material genome is very, very important. And also in China, we call this material genome engineering. Based on this background, we think we need to focus about the building multi-source data. For example, we need to use the mechanic data, the electrochemical data, also the microstructure. We need to try to put all the data together to make a decision, or some from the data aspect, we need to analyze all the data related to the performance. So that's why it's very, very important rather than relying on a very small amount of the data samples of the conclusion. So that is the one change in the material research and development by the MGE method. And another one is about the data of the material structure, and properties need to be screened and modeled with the help of computers. So I just put two Nature paper on this slide. You can see the one is sharing data in materials science, and another one is published by Professor Lee, called that we need to share corrosion data. So after that, if all of us, we can share our data together, maybe we can find some new mechanism. So the third one is about the experimental tools for the automatic in situ method, and also some computational tools for the multi-scale modeling and the data analysis tools are very, very important parts for the MGE study. So based on this, I think what can the calculation do for the corrosion? Maybe we need to, from the thermodynamic and also dynamic and the electronic, from these three parts, maybe we can know something new. So by the meaning of the integrated computational corrosion, so I think maybe the cross scale, the general additional information experience to the model change from the known to unknown. Maybe the creative and the new things is very important for the corrosion mechanism. And with the tendency, we need to use the new computer technique. For example, the self-learning and the optimizing for the corrosion resistance. And the key point is we need to use some committee to get the standard. So after this standard, we can share the data. Without that, it's very, very hard to do. After that, we want to establish extensible modeling and very useful models to develop open the integrated computational corrosion platform. So based on this, because the time limitation, I want to show some examples about our work. If you want to know more in detail, we can use the email, or after this conference, we can use other, for example, the Skype to communicate more. So the second part is about the integrated computational corrosion. The first one is about the use the DFT calculation to get the pore diagram. From the reference, the pore diagram can be calculated by different kind of the softwares. For example, the material project, the SimCalc, and also the Pemagine. We also know many groups. For example, the Dr. Huang Liangfeng and in the group of the Professor Scully, they also do very perfect work about in this part. In our group, we want to use the Python software to to face the challenge. The one is the binary and the ternary OR system, and we want to use the method to calculate some complex solution system. So how to get very fast and efficient results? That is our work want to serve. So with this based, we also make our software. You can see on the right hand is the Python code, and after that we just follow several steps. The first one is the chemical potential of the solid phase, and also we use some different we use the experimental chemical potential together combined with calculation results. So that's why we can solve some very complex system. So the chemical potential of the aqueous ions from the experimental chemical potentials, we use this equation, and after that we also to try to write down all the equations and the reactions during this system to use the DFT do the calculation. The results show we can do the ions, chloride, and the H2O system. So that is a new aspect in our group. So this is from the thermodynamic method. And the third one is about the passive film stability. This one is guided by the Professor Digby McDonald. So the first, we use the electrochemical test and also use the PDM model to do a lot of analysis based on the experimental result. And after that, we established several kind of the passive film models with the point defect inside it. So after that, we can get the corrosion resistance, the changing of the film formation stability. So And we also focus about the different kind of the semiconductive character. You can, from the table, we can know the diffusion composite from the electrochemical method, and this list is from the PDM model, and this one is from first principles calculation. We know that the diffusion composite is the results show very good consistency with the diffusion composite of the copper vacancy being the range of the 10 to minus 15 power to the 10 to minus 14th power. So from that is very good for our experimental temperature in this system. We also published the paper in the Corrosion Science, and after that we try to use this method to calculate different kind of the passive film. In the various passive films, the diffusion composite changed greatly, so we can use the diffusion rate of the point defect as the key dynamic parameter. Also, we use the band structure about another different kind of the method to do the HICE. That is, we can get more accurate result for the band structure. This one shows the combination result of the calculation and the photoelectrochemical experimental verify that the increase of the copper vacancy concentrate in the passive film would be substantial indeed owing to the precipitation of the chloride ions. So from the left hand, we use the calculation model, and on this part, we use the experimental to get the result to see whether the result can agree with each other. If we can know after that, we can use this model to do some evaluation and estimation. And the third one is about the hydrogen diffusion behavior in the 2205 duplex stainless steel. This task belong to is get by the Professor McDonald and Professor Mirna. We try to use the original fake Leis to establish this equation, and also use the reversory hydrogen trap to modify this fake Leis. And after that, we do a lot of tests with the parameters and the result of the hydrogen permission. This is from the experimental. After that, we use the console software to establish and simulate the hydrogen diffusion inside with the stainless steel. So after that, we can just get different kind of the boundary to do the hydrogen concentration, to get the hydrogen concentration distribution with respect of the time along the thickness and the samples. And for the time limitation, this part is just very fast to get. The fourth part is about the cross-scale calculation of the atmospheric corrosion. We use the first principles to get the hydrogen, and we get to use the atom diffusion and absorption behaviors, and then input the parameters into the pyrodynamic theory. And after that, to use the transform parameter, input the cohesive interface, the green boundary energy as the transitive film parameters to the finite element method to get the cross-scale calculation. Within recent 5 years, we already use a lot of the supercomputation, the center, and we also set up the software. So sorry for this conference time for me. We didn't change the softwares into the English version. Maybe next time. We also calculate all the elements in the tables, and we within the database we give a lot of the details, and also within different kind of the material. Within this system, we give the calculation data, the mechanics, the microstructure, the electrochemical, and after that, some machine learning method also within this software. You can just submit your postcard and your postcard field, and you can get some estimation. So we already have 2 million data in this system, and maybe after this we can use some machine learning or some other computer tools to get more results. This is about use this method, different kind of the k-nearest neighbor and the decision trees. We try to analyze different kind of the polarization curve and also EIS data. After that, we choose the random forest as the best one to do the estimation. And this part is about the recent work we just carry on. This is published result. This one, we just want to use the DFT modeling assistant with the AI training for the outdoor exposure quotient data. And because for me, I can get a lot of the exposure data, but the accuracy is not good enough to meet the requirement for other users. So that's why we just put the DFT calculation of the compounds. For example, the aluminum alloy, there are maybe 2000, 5000, 6 and 7000 series. So we can use the calculation as the input and get very good results. They can the error between the predict and the experimental corrosion rate of the aluminum alloy in the Southeast Asia is less than the 15%. So that can be used. And the third part.
3 minutes. Can you quickly speed up?
Okay. The third part is about the computing assistant improve of the corrosion resistance. So for other speakers already mentioned about the inhibitor, so this one just use the calculation and also the thermodynamic, also some molecule dynamic, and we use the experimental to verify our result. So that follows about all the MGE. The floor. This one is about the high throughput calculation. We just use to screen the potential alloy elements that can increase the resistance for the stress corrosion cracking. This one is about the different kind of the dislocations moving, so we can investigate about on the green boundary and also the integration. For example, the ether and the ether prime phase precipitate and the green boundary, the dislocation may plug effect of the green boundary is no longer observed, and also the strength of the green boundary change a lot. With the interaction of the hydrogen atoms, everything changed. If for more details, you can see our papers on the corrosion science. So this is about the selective laser melting design. All the part of the result calculation, we use the experiment to get the whether it is true or false. The last part is a peek into the future. So this is the our part from the atomic simulation to the engineering part. So from the calculation line, and also we use the experimental to do the verification. This is different challenge, and we want to use different kind of solutions. And now we are looking for the cooperation. The first one is about the Probex diagram. We want to use Professor Digby's kinetic stability diagram to do the modify. And the second part we look for the cooperation is about the reactive molecule dynamic. We want to we need the force field of the aluminum, carbon, hydrogen oxide, and chloride. So in the future, if you're interested about this field, we can make more communication. So the question is very, very challenge. So it's very complex and very cool. Thanks for all the professors, all the group members help for us. And that's all. Thank you.
Thank you very much for the excellent presentation. Because of the time, I just have one quick question. Is there a standard or guideline for effective application of integrated computational corrosion analysis?
Thank you, Professor Cheng.
Can you recommend any book or any guideline for the research to get used to your research method in terms of the corrosion computation?
And now most of us, we use the book from the ICME that belong to the MGI program. So maybe in the corrosion, we want to just organize a group. We can make our books, but the standard is very challenging.
Excellent.
Yeah.
Excellent. So Digby also give your comments. Okay, so you can read the comments from Digby by yourself. All right, so thank you very much. So if anyone have any further question, so probably will feel free to have the communication. So we just switch to the next speaker because of the limited time.
Thank you.
All right, so yeah, thank you. Our next speaker is Dr. Brian Leis. So Dr. Leis is kind of the benchmark person in pipeline integrity management, have a big contribution in terms of the technical development in the area. So the Dr. Leis will present the pipeline integrity management based on the inspection data analysis. And so next we give the time to Dr. Leis.
Thank you for the invitation to speak today. As Frank said, I'm going to talk about condition-based integrity management, specifically in regard to pipeline systems. 4 or 5 major topics, some background. I'll then take some time to talk about level 1 assessment criteria. I'll present a case study. I'll then talk about some of the issues that remain in terms of dealing with real corrosion versus idealized corrosion. And I'll close with some dialogue about conclusions and takeaways. So by way of background, we're in a conference involved with corrosion. Corrosion remains a major issue on pipeline systems, in spite of the fact that we've had controls in place for literally decades. Roughly 20% of the failures in the United States are caused by internal and external corrosion. Not surprisingly, corrosion initially was the major cause of failure, and it was the initial focus of technology development for integrity management for pipelines. The initial regulatory focus was on ensuring a conservative failure pressure, and recently that was extended to consider a response time and revalidation issues, intervals rather, which open to concern for corrosion rate and defect size. By way of explanation for why these regulatory drivers cause problems, if you think about the fact that the failure pressure is a function of a constant, which is basically the reference stress in the pipe geometry, and the effect of the defect, if you change one side of this equation, you have a corresponding effect on the other. So historically, by making things conservative, the bottom line was if you decrease the failure pressure through conservatism, you effectively decrease the defect's length. But once the time came to consider the influence of defect length, a shorter defect length gives rise to a longer life. So you really have to have these two parameters in balance. We need to keep the failure pressure and the defect size in balance, and that demands a very, very accurate solution. And you can see that in the context of the chart here. This data point represents a point. If I reduce the pressure by the amount indicated and then track up the green dash line, you see that I'm substantially shorter in terms of the defect length. So there's a clear concern in this context for that influence. And I do want to point out that I'm using a reference stress here that's a function of the UTS and the strain hardening exponent that has its a theoretical foundation in power law plasticity for those that are interested. Talk briefly now in terms of cost, safety, and conservatism. And I'll note that any conservatism that's introduced to offset model error, and that's why it was initially introduced, that does not really add any safety or reduce risk. It simply offsets the model error. So the costs associated with model error management can be removed without altering, much less jeopardizing the safety of the system. And the key cost management driver in this context is an accurate, precise solution that eliminates the need for the conservatism. Bottom line in terms of the prior chart was that you could not have a margin of safety applied prior to doing the analysis, but if the analysis gets done correctly, you can add that margin of safety in afterwards. And the objective of our work has been the development of accurate, precise mechanics, science-based models of failure pressure to end the money wasted on offsetting model error. I'll talk briefly now about level 1 assessment criteria. And I'm going to focus particularly on issues later in the context of idealized versus real corrosion, isolated corrosion versus complex corrosion, and detection and sizing. And throughout our work, the premise has been that if a criterion is inaccurate for an idealized isolated feature under well-controlled testing, then such criteria don't provide a sound basis for technology development. That's really been fundamental to our path forward. So if we look historically at predictive methods, and the upper box here focuses on defects, you'll see there that we've got a comparison of some early criteria, B31G and modified B31G, versus some more recent criteria, PCORC and a more recent version of PCORC. And the big difference here is evident. There's significant bias present in these predictions. That bias tends to be removed and the scatter reduced by the modern criteria. So there's a big step between the early and the modern. But if you compare a lot of the modern criteria, they don't discriminate very much differently. They all have their roots in plasticity theory, or generally have their roots in plasticity theory, and as a consequence of that, have more or less comparable errors. If we turn our attention now to defect-free pipe, remembering that the failure pressure is a function of the pressure of failure of the pipe that's defect-free, coupled with the effects of the defect, it becomes apparent that for these early criteria, much of the bias that's evident here is a consequence of the bias that's present in the reference stress. In comparison to that, if you look at the more recent criteria, you see that the bias is much reduced And you see that the scatter is significantly reduced when we use a failure criterion for the reference pipe. That's a function of the UTS and the strain hardening exponent. So the observations are as noted here. The early criteria were scattered. That's well known. The recent criteria are much improved. But if we dig into the details, we quickly see that there's work still needed in terms of the defect term, particularly in regard to selective width effects. Historically, failure criteria have used reference stresses that were very conservative, as was evident in the prior chart. The purpose of this chart is to illustrate the role of strain hardening exponent and in regard to failure pressure. And we see on the ordinate here, in both cases, the same ordinate. It's a normalized failure pressure where the pressure is normalized in the context of this normalization parameter, which includes the material UTS, the pipe diameter, and the pipe wall thickness. And what that allows us to do is then compare failure criteria for defect-free pipe. These are test data for defect-free pipe across a range of materials and pipe geometries. And what you see in both cases here, two different data sets, is that the data follow a clear trend as a function of the strain hardening exponent. And you see it here, there's a swing of roughly plus minus 10%. Similar results here. Bottom line, and it's really the critical piece of this from the point of view of predicting failure reliably in pipeline systems. We have a wide range of grades that fit this model, from the earliest grades to the most recent modern grade. This happens to be a Japanese steel that's close to X120. Covers a wide range of diameters and covers a wide range of wall thicknesses. So plus minus 10% is 20% in total. That's not a trivial error in predictions for failure pressure. So N is clearly important in this context. I want to talk now briefly about the influence of defect width. For those that are familiar with failure criteria for corrosion and pipelines, they're primarily a function of the length and the depth of the defect. They completely ignore width. And yet if you think about width, the width being the dimension around the pipe, if you think about the width relative to the length, features that are large in area will bulge significantly, whereas features that are, for example, narrow but long don't bulge much. And what you see here for the same depth, this happens to be a feature that's 80% deep. That's the maximum allowable by code. You see a difference in the failure pressure as a function of the width. That, in this case, amounts to 195 PSI. So there's a width effect for deep defects, but if you look at the same scenario in terms of length and width, but now consider just 10% depth, the outcome in terms of failure pressure is identical in both cases. So there's no width effect. Importantly as well, if you look here, the highest stress occurs in the middle of the defect, whereas for this feature, it occurs near the edge of the defect. So the hot spot for corrosion is shifting, and that has implications for detection and sizing. It has a significant effect. Here, the width effect is a function of depth, but the width influence is selective in regard to the length. It's selective in regard to the aspect ratio, that is to say the length to the width, and other parameters. So width can be a very complicating factor, and unraveling why it's a complicating factor turns out to be relatively simple if we contrast these two scenarios, the wide and deep versus the wide and shallow. You see here that there's a relatively gradual transition through the full wall into the part wall of the pipe. Whereas here you see a very significant transition, and you'll see in this context here a very, very sharp change in the transition across that interface, and it's coupling bending and membrane tension here, where it's largely membrane tension here. And that's why width is a factor. Historically, we've ignored it, but as you can see, Width was a significant influence, and next generation criteria will explicitly embed width effects as we move forward. I want to deal now with a case study. And that case study focuses on axially aligned internal corrosion. It's in a condensate pipeline. And on the left side of the figure, we have defect population plotted in terms of its length and depth. We're looking at the leading edge of that population because that's the part of the population that controls failure. And I've got two predictions here. So the indications are found by the inline inspection tool. That inspection was validated. One of the failure criteria here is the early failure criterion, B31G. This criterion here is PCORC, and actually the revised version of PCORC as well, because for this particular case, the strain hardening exponent versus, a criterion with strain hardening exponent in the UTS differs a little from that of the early work that was based solely on the UTS. What you see in this band between these two criteria is roughly 60 features. This criterion required that certain features be fixed. On all of these above and close to it were repaired, and then the line was hydro-tested and passed. So this criterion was proven viable in a real-life application. The bottom line here is that if you look at the number of features that you don't have to deal with using this criterion versus this criterion, this one's accurate, this one's very biased. By saving or by avoiding the modeling error, we've avoided, in this case, digging roughly 60 features and repairing roughly 60 features. But if you take the corrosion rate that was active here and advance this population in length and depth, what you see very quickly is that you'll add a tremendous number of features such that 60 becomes 600. The benefit in this context of using an accurate, precise criterion is that you've significantly reduced the number of digs and the follow-up maintenance that's required. For those of you that are interested in the details, it's covered in the journal that Frank edits, the Journal of Pipeline Science and Engineering. Those details are in that paper. Let's look now at a path forward and issues that remain to resolve. And this is an important chart because I'd like to talk about idealized versus real, and I'd like to talk about detection and sizing, and I'd like to talk about isolated versus complex, but the time remaining, roughly 4 or 5 minutes, says that I need to focus on one of these, and what I've done is chosen isolated versus complex, because the reality is you can have isolated versus complex issues with idealized features or real features, and you can have detection and sizing issues with both of these. So this tends to be a good place to start. Complex in this context refers to the interplay between corrosion features, and I have an example of 2 clusters of corrosion on a pipeline. It's a 24-inch diameter pipeline. You can see the bottom side of the pipeline here, top side's roughly in this vicinity. And isolated features, this cluster of corrosion is isolated from this cluster of corrosion by the full wall thickness. So we talk about this cluster interacting with this cluster because it's separated, or they are separated rather, by a full wall thickness. So we use interacting in that term, in that context. But you can also see features here. Here are 2 pits side by side that are overlapping, and they're surrounded by a full wall thickness. And we say those features are coalescing because they are already overlapped, and whether or not they fail occurs by their length increasing by their coalescence in failure. So these are different scenarios, yet they're both dealt with by boxing or clustering rules in this detection and sizing world. The key in the context of corrosion like this is the realization that the stress fields and the gradient between the features control the consequences of failure. And for those people doing risk management, consequences mean everything. So, and I would say as well, you don't have to be doing risk management to worry about consequences. If you're operating a liquid pipeline and it leaks in a significant way, the public and the environment both suffer. So it's not just a matter of risk-based decision making. I'm adding two plots or two charts to this, which show a feature very similar to what you see in this image here, where we have overlapped pits, and you can see here's a pit and here's a pit. These are really pits within pits. You see a lot of little pits here. These pits are growing by virtue of smaller ones giving rise to a bigger one. This is not quite a full wall thickness. It's a significant barrier, if you will, between this feature and this feature coalescing or failing in a shared way. Notice here that the depth, maximum depth, in this case, this one, is 0.53. The same is the case for this pair. In this particular case, this is a slightly shorter feature as compared to this one. This is a view pre-rupture. As you can see here, leak paths have formed, and this is a post-leak image. This combination leaked because the barrier between these two features was relatively shallow and they could coalesce. As they coalesce, they fail at a lower failure pressure. But because these two features are relatively resistant to failure, they don't coalesce and they gave rise to rupture. So the significant difference here is a leak, which is a relatively small release through these very, very tiny cracks. Remember, this feature is just 2 inches long or a little less than 2 inches long. So this is a critical element of the problem. I'm at about 18 and a half minutes, so I'll move on here. My last chart, Frank, takeaways and conclusions. As I've discussed very quickly, width as well as strain hardening rate can significantly affect the failure pressure. And it can be a reduction, and that's the critical part of it. Reduced failure pressures as compared to what you predict are very bad news. The strain hardening exponent can cause swings in failure pressure to the order of 10% or more. Width can cause swings in failure pressure of several hundred PSI, not trivial. Width effects are selective. Many parameters affect that selectivity. And we need a criterion to be developed that will address these aspects in a very robust way. The upside here is that the Pipeline Research Council International is working to develop a criterion to address these remaining issues. They include the interface with inline inspection, width effects, interaction and coalescence, and real corrosion, and so on. And that's a key piece as we move forward, because that's going to bridge a currently significant gap. And the final point to make is that we have now made significant strides in comparison to the early criteria. We've reduced predictive scatter. We've tightened that in the context of defect-free pipe, as well as the effects of other factors. So we do have simple predictive schemes. Everybody will say, well, where do you get the strain hardening exponent from? We do have very simple schemes now that provide tight correlation between N and Y over T, and those are in hand now. So these new criteria can be used as people choose to employ them. And with that, Frank, I'll try and get you back on time.
Thank you very much, Brian. So it's a very good presentation. So right now I have 2 quick questions for you. The question number 1 is, what is the length to depth ratio to classify a defect as localized?
Length to depth ratio classify localized. That's a good question. The defects that tend to fail at the highest failure pressures tend to be small, physically small, and geometrically similar in shape. So a pit, a relatively small pit, can be very, very deep and still not fail. So length to depth in that context would be close to 1 or 1.
All right, so another question is, will temperature infect the pressure contaminant ability of the pipelines?
So if most pipelines in service are buried pipelines, and they're very moderated by the ground in terms of their temperature, even though they've got a warm product flowing in them. Temperatures tend to be less than 140 degrees, more or less in that context. Temperature is not a big factor in under those circumstances. It does affect corrosion rate, obviously, but in terms of failure pressure and mechanical properties, it's not a big driver.
All right. Okay. So again, thank you very much, Grant, for your excellent presentation. And I believe the pipeline people will learn from your talks. Okay, so because of the time, we go to the next speaker. It's following Brett's presentation, we invite a research focus on the risk assessment. So Dr. Markus Dann is a professor of civil engineering at the University of Calgary. So the Markus is expert as the risk assessment of pipelines. So next, time to Markus.
Hello, everyone. I'm very happy to be here today. And as Frank was saying, my area is pipeline risk assessment. Over the past 2 years, I've been focused extensively on risk-based assessment and inspection maintenance planning of corroded pipelines. So I want to present some results and create a little bit of awareness of the problem. I really appreciate the 2 previous presenters because they were pointing out some very important issues related to corrosion modeling, but then also to, okay, how do you manage the pipeline integrity? So let's briefly look at the life cycle of a pipeline. And it's a little bit different than what it's usually presented because I'm looking mostly from an integrity perspective. So we have the pre-service period, we have the pipeline in service period, and we have the post-service period when the pipeline is out of service. Pre-service, that would be the planning and the design stage and the construction. That is not really interest from my perspective. What I want to focus on is pipeline during service. As the pipeline is in service, we have all sorts of deterioration mechanisms that develop over time. And we're in some sort of a cycle throughout the service life of the pipeline where we have inspections. They tell us, they basically give us a screenshot of what is happening in the pipeline in terms of damage. And then from those results, we take them to the analytical integrity assessment stage where we assess the data, we correct them for any possible bias that come with the inspection data. We will see that in a second. And then we need to assess how critical the defects are. That goes back to Dr. Leis' presentation. Let's say we can use a level 1 analysis to assess, okay, which one needs repair, which one are still okay. And then based on that, we make decisions in terms of what type of maintenance is required, how many defects need to be removed, how many locations need repair, and so on. And this cycle of inspection, analytical assessment, and maintenance is repeating itself every few years throughout the entire service life. So that's basically what I want to talk about, those 3 points here. I want to focus mostly on the first 2 and what happens in terms of corrosion assessment. So pipeline inspections. The most common version are the so-called inline inspections, where we have these pick. You saw a picture on the previous slide that is sent through the pipeline. And then depending on the techniques, They detect and size the features and the anomalies in the pipe wall. So we have different techniques available. Probably the most common one is MFL, magnetic flux leakage. We have UT, eddy current, and so on. But MFL is probably the most dominant technique when it comes to pipeline inspections. As I already mentioned, the objective is to detect the features in the pipeline. So where's the location where there is a damage, and then also says the extent of the damage, basically in terms of size, like how deep is the feature, how long, how wide. And those tools are able to do this and distinguish if the defect is happening on the inside, if it's internal corrosion, for example, or if it's happening on the outside of the wall. Now, all these techniques, they are non-destructive techniques, so there is a lot of signal processing involved, and this is usually done by the ILI vendor. So they do the initial signal processing, and then they generate a list of all the features or anomalies they found in a pipeline. And I will show you an example on the next slide on how this looks like and how simplified this the corrosion is presented and basically what the operator has to move forward. Then with those list of defects or features that are detected, then they're used to assess, okay, what is the actual corrosion growth in the pipeline? And then from there, we can assess the likelihood of failure. So inline inspections are usually used for full scans of the entire pipeline. And then we have the possibility to follow up. And that usually happens when we have decided where we need maintenance to do local inspections. Those local inspections are done from the outside, which means if it's a buried pipeline, you have to excavate it. You really need to get full access to the pipeline, to that specific section. And then you do a local verification inspection from the outside, where you can scan with a very high resolution a small section. And those results are used for two purposes. One is to verify the location where you actually want to do the repair. So if that was a location that was initially flagged as a very severe corrosion in terms of extremely deep, or in terms of the shape that there is a high risk for burst, let's say, we want to make sure we're actually repairing or doing the repair on the right location. At the same time, we can use those results to update the ILI results that we received earlier and see if there might be some adjustment necessary for the full inline inspection. So from a pipeline operator perspective, once the inspection is done, they typically get a list that looks like the one here at the bottom of the slide. It comes usually in an Excel spreadsheet, and each feature that they detect gets a number. Then they say what feature type it is. So in this case, metal loss, that would refer to corrosion. And then the other information, we have the log distance that basically tells you how much down the pipeline was that feature detected, the clock position, and then we obtain the length, the width, and the depth. And then in the last column here, we have if it is an internal feature or an external feature. So this is typically the start point when we do the analytical integrity assessment, that we have these Excel tables available from the ILI vendors. And then every few years, as we do a new inspection, we get a new table. And then based on this series of tables, defect matching needs to happen. And then we can infer, okay, what is the corrosion growth? And then assess how critical the defects are. So here in that sample pipeline that I've drawn, I mean, we have seen also in earlier pictures, corrosion can come in sort of any shape. What we get here as a result from the inspection is more like the length, the width, and the depth. It's just three values that describe what is happening for one defect location. So this is usually the maximum length, the maximum width, and the maximum depth that they provide. So often you see in a lot of models, we then assume, okay, the defect is just some sort of a rectangular box with a parabolic shape, or even like a full box that describes the metal loss in terms of the geometry. So the point here is the exact corrosion shape remains unknown. We don't know it. We just work with those three values, length, width, and depth. The most important one would be depth, as we have seen earlier, to do, let's say, leak assessment and so on. So then based on this, we now need to go to the analytical assessment, where we have two things to do. One is we need to do the corrosion growth analysis. So we need to assess what is the current corrosion size, what will be the future corrosion size, and then assess, okay, how critical the defects are, or when do they become critical? How much time do we have to follow up in terms of inspections and or repairs? And in this feature assessment, what I call it, we have different ways of doing this. As we saw earlier, the level 1 assessment is some sort of deterministic or code-based. It is usually based on conservative values, and it just gives you a yes or no answer. Is the defect acceptable? We can still leave it in. We don't need a repair. Or it is very close to be critical, so we have to follow up. That is one method where we're not really directly addressing the uncertainties. Now, if we want to do a step better, we can do it reliability-based. So for each defect, and then for entire pipeline sections, we determine the probability of failure. So now we're going away from a deterministic analysis, or an analysis where we use fixed numbers, to more like a probabilistic analysis. So we really want to describe explicitly what are the uncertainties. And then we use the failure probability and compare it with a target failure probability. And as long as we stay below, we say, okay, the defect is acceptable. If that's not the case, then we have to follow up. The next step up would be, or in this case on the table down, would be a quantitative risk analysis. I mean, we also have qualitative risk analysis. I don't want to address those. I really want to focus here on the quantitative part. So again, it relies on a probabilistic analysis, and then we can assess societal, economical, environmental risk of failure. We will see towards the end of this presentation a little bit more, especially in terms of economical risk of failure. And then the most advanced analysis would be some sort of a benefit minus cost minus risk. That's some sort of the equation that has been used, or in more general terms, a cost-benefit analysis, where we can then determine, okay, what is the best way forward, considering all the possible costs that we generate if we have failure, all the possible costs we generate due to inspections, maintenance, and so on. And then in this case, the results are really analysis dependent. So my point is, as we go forward, we want to do it risk-based or even reliability-based, we need to do a probabilistic assessment of the pipeline. In terms of corrosion growth, we have several options to model that. And we have seen earlier that, I mean, we can have these very advanced mechanistic models that really try to model the electrochemical process. And I'm not really an expert in that area, so I don't want to comment too much about it, but we have seen those models can be very extensive. But when it comes to pipeline applications, usually we don't have all the information available to use those advanced models. Then the next group would be the so-called semi-empirical models. Like I used here as an example, the CO2 corrosion model by Devort. Also not very often used when it comes to risk assessment of pipelines. In this case, it is more like that we rely on so-called empirical models just simply based on the available inspection data. And then if it's some sort of a probabilistic analysis or a probabilistic corrosion growth analysis, we need to decide how do we model the corrosion growth. In industry, we see most commonly the corrosion rate model. Like so much percentage of wall thickness loss per year, and then you multiply it by the time interval, and that gives you the metal loss over a predefined time interval, for example. So if you use the corrosion rate model, and now because we want to explicitly model the uncertainties, we make the corrosion rate uncertain. So that means then we grow with different slopes here in that uncertain corrosion rate model. That is one way to go. Or we can use so-called stochastic process models, where we say, okay, at the time of the inspections, we know how much metal loss we have in the pipeline. And we're just worried about how much the jump or the increase in metal loss is from one inspection to the next. How much or how we get from one inspection to the next, what the exact shape of the metal loss is, if it's linear or non-linear or any other form, doesn't matter. So if you compare the model on the left, the corrosion rate model on the left, with the stochastic process model on the right, the stochastic process model from an uncertainty perspective is really the right way of analyzing ILI data. On the left, where we assume always a straight line with an uncertain slope, does not represent the proper corrosion growth. Also, they're preferred in industry. They're relatively simple in terms of the mathematical handling. From a probabilistic perspective, an uncertainty perspective, they do not capture probably the temporal uncertainty in the corrosion growth. So our focus when it comes to actual application should be the application of stochastic process models to model the actual corrosion growth over time. So the actual corrosion growth over time, that is one major uncertainty when it comes to predicting the future defect size. And then we have one due to inspection errors or measurement errors. And there we have several types that are some sort of already built in that list of defects that we obtain from the ILI vendor. We can have detection errors. So out of all the defects in a pipeline, not all of them are detected. And to describe that, what is happening probabilistically, we have we use a so-called POD, probability of detection curve. As a defect is large, then the probability of detection is very high. So there's a high chance we will actually capture those. Usually POD is very low when it comes to defects that are very small. That's relatively good for us because the smaller ones, we are not as worried from an integrity perspective. So, but we have to keep in mind the list of defects that we have is not complete. We're still missing some that are not included. Then the next type of error we have is a so-called sizing error. That is, the actual size in the pipeline, let's say the percentage of wall thickness, is different than what the tool is telling us. So here is a scatter plot where I have the actual size in the pipeline on the horizontal axis and the reported size on the vertical axis. So if you would have a perfect tool, all those defects, they would lie on this one-on-one line, on the green line here. As you see, that is clearly not the case. There's quite a spread and quite some sizing error contribution when it comes to corrosion growth. If you assess the corrosion growth based on the change of the measured size, you often see that close to 50% of your defects don't grow or they have a negative growth. And this negative growth is just due to the sizing effect because it is so dominant. We then also have identification errors. that we think, okay, this is a metal loss or it's a different feature type and it's not classified as a metal loss. Those happens as well. And then the ILI vendors, they usually cut off very small defects and don't report all of them, just simply because the errors on the very small ones are so large that say, okay, they're not very important, we just leave them out. So based on these lists we saw earlier, that are obtained from the ILI vendors, before we can actually determine the corrosion growth, we have to consider all of these effects here before we can do the analysis. So here's just an example where if we consider a stochastic process for the actual corrosion growth, we include all the measurement errors. We have here in the left figure on the horizontal axis the time. We see here the ILI measure points. And then we see here the predictions. The full lines are the mean values, and the dashed lines are sort of 80 or 90% confidence interval. So as we see, as we go more and more in the future, our confidence increases, or the confidence interval gets wider in terms of what is happening for the metal loss. Based on this, we can then use so-called limit state functions to assess what is the probability of failure. So here on the right, I have an example where those defects on the left were assessed in terms of leak failure. And then we can estimate the probability of leak failure as a function of time. So as the defect grows over time, we see the probability of failure increases. And then if it's a reliability-based assessment, we can say, okay, once we hit our maximum allowable failure probability, that's a time, or before that, we have to intervene. All right, reliability targets. So this is an example from the Canadian pipeline code on how much or what a reliability for a pipeline system looks like. And this is almost a surrogate for risk analysis, because on the horizontal axis, we have three variables that go into this product. We have the population density as a measure for the consequences, or how many people would be affected if there would be a pipeline failure. And then we have pressure and diameter of the pipeline. In terms of bigger pipelines, usually cause larger consequences when they fail. And then we see here on the left the target reliability, which is 1 minus the probability of failure measured per kilometer and year. So we see smaller pipelines, they have a higher failure probability. And then as we get to larger pipelines in more populated areas, the failure probability needs to be reduced.
Markus,
you have
almost 2 minutes.
2 minutes, that's good, I have 2 slides. So the previous slide, we saw the reliability-based version. We can do it similar risk-based, or then overall use that risk also in a life cycle analysis, or even, let's say, a little bit shorter than a life cycle analysis. So in this case, the objective function would be in some sort of the benefit of the pipeline minus cost due to inspection maintenance minus the risk, and the risk would be a function of the probability of failure and the consequences. Typically, when it comes to pipelines, we ignore the benefit part. So we're just focusing on cost and risk. So what we want in the end to minimize is the cost we spend on maintenance and inspections and the risk that we still have due to failure. It's clear, as more money we spend on maintenance, we reduce the risk. The less money we spend on maintenance inspections, usually the higher is the risk. But there's some sort of an optimal point in between, and that's shown here on the right, where this cost and benefit, this black line, reaches a minimum. And this was where we would like to operate the pipeline. And based on this point, we can make decisions in terms of when to go out and inspect again, where to make repairs, if it is worth having follow-up inspections, and so on. All right, conclusions. So in general, and from the industry, there's a clear trend towards quantitative risk assessment. Really, the objective is to minimize the total life cycle costs from an operator perspective and still keep the pipeline safe. And that is often used then to prioritize where to go out and make repairs. Those defects that have higher risk, you prioritize first. Those that have lower risk come a little bit later. Now, when it comes to corrosion growth, it is typically or primarily inferred from ILI results. And I definitely see, or I wish there would be a stronger integration of those more like advanced corrosion models, like those where fall into the mechanistic corrosion models, into the actual risk assessment. I've showed you some very basic examples. We use relatively simple probabilistic models. We don't really consider what is the actual mechanism behind it. There's still a huge gap, and I hope in future we can close that. From a temporal uncertainty perspective, we should avoid corrosion rate models. They're not really accurately present the temporal growth over time. And it is possible that based on the ILI measured growth, that this be negative, and this is due to the strong influence of measurement errors. So that doesn't mean there's no growth. It just means the measurement error is so significant there can still be a small or even quite a significant positive corrosion growth of the actual defect. So thank you very much.
All right, thank you, Markus. Okay, so Yuan is a little bit behind the schedule, but I still have one quick question for you.
Sure.
How often and what's the frequency is inline inspection conducted?
It really depends. Typically, I would say it could be in the range of 3 to 5 years.
Okay.
And this is when it comes to forecasting corrosion growth, you're not really looking for a window of 10, 15, 20 years, because you have usually in 5 years, you have a follow-up inspection. So a defect that is not critical right now, and if it's not critical in 5 years, you can then catch it before it becomes critical. So that window that we're looking at is usually up to 5 years.
Okay. Anyhow, so we have another question. Can you give a quick answer, please?
Sure.
What is the best method to compare two inline inspection results to give a representative corrosion rate?
All right. Okay. That's quite an interesting question. What I would do is match the defects and then compare them without any probabilistic analysis. And usually you will see there is defects that are very large at the beginning. They're very large in the second follow-up run. They still have a relatively large growth. This corrosion growth rate is usually a relatively good number. I wrote a paper on that in 2014, presented at IPC. If whoever asked that question, if you want more information, please send me an email. I'm happy to follow up. That's my short answer.
Okay. Yeah. Thank you very much, Markus. Excellent.
Thank you.
Thank you. Yeah. Okay. So let's move to the next speaker. So next speaker is Dr. Milos Djukic. I'm sorry. So please excuse me if I pronounce your last name wrong. So Milos is a professor with the University of Belgrade, and he's reputed research in hydrogen and theory and modeling. So Milos will give a talk focused on the assessment of hydrogen embrittlement. The time is yours, Milos.
Dear colleagues, ladies and gentlemen, my name is Milos Djukic. I'm an associated professor at the University of Belgrade, Faculty of Mechanical Engineering from Serbia, and I will present you invited talk. Thank you, Professor Frank Cheng, for inviting me, with the title Assessment of Hydrogen Embrittlement and a Model for Structural Integrity Analysis. This is a mutual work of University of Belgrade, Serbia, and also the participants from the University of Melbourne from Australia. Here is the presentation content. First, a little bit about hydrogen materials interaction. Then I will present the recent results related to the synergistic action of hydrogen embrittlement mechanisms in steels and other materials. Then I will present our originally proposed model for hydrogen embrittlement in 2014 and 2015, HELP plus HEAD model. Then structure integrity model based on this model, and finally some conclusions. Here is the sources and our references related to this presentation. I wish to point out the book for Elsevier in preparation, which will be published in 2021 together with Professor Branko Popov about hydrogen embrittlement theory and prevention of hydrogen damage in metals and alloys, and also our future paper International Materials Review with a group of top scientists related to hydrogen embrittlement, which is also in preparation, and 3 important papers related to HELP plus HEAD model. Hydrogen materials interaction is a complex term, but if we talk about preventive maintenance and talk about maintenance engineering, they are mostly interested in these terms. That is the hydrogen-assisted cracking. What is the hydrogen-assisted cracking? Hydrogen-assisted degradation of crack propagation resistance by assisting the microscopic process that constitute crack tip advance. Due to the degradation of a crack propagation resistance, the components finally failure. On the other hand, hydrogen embrittlement is restricted to the perception of precise nature of the hydrogen-assisted mechanical degradation, and we have various models on which the degradation of crack propagation due to hydrogen embrittlement exists. In our recent review paper published in Engineering Fracture Mechanics, we proposed a 5-step approach in analysis of hydrogen materials interaction, which consists of phenomenological analysis of hydrogen-related degradation phenomena, different experimental and modeling approach in order to finally reveal the hydrogen embrittlement mechanism active in a particular material. Next is the analysis of hydrogen source and entry, where the corrosion is the main process which provoked hydrogenation of material during the exploitation of various industrial components. And based on such analysis, we provide and develop a structure integrity model based on the multiple active hydrogen embrittlement mechanisms active in steels and other materials, and connected with the micromechanical response and behavior upon the reaching of the critical hydrogen concentration in material. Future works will be focused on predictive maintenance model based on NDT characterization in order to provide a reliable and accurate life damage prediction of components exposed to hydrogen embrittlement in various industrial plants. So we have a missing link between numerous phenomenological research of hydrogen metal interaction and practical and predictive industrial models. We could say that a fully developed and practical applicable predictive physical model still does not exist industrially for predicting and preventing hydrogen embrittlement. The synergistic action in hydrogen embrittlement mechanism was recently divided into 2 major models. The first one is HELP-mediated HEAD model about the synergistic of hydrogen-enhanced localized plasticity and hydrogen-enhanced decohesion mechanism, and our model HELP plus HEAD proposed in 2014 and 2015, now relatively very well accepted, which indicate that the dominance of one of the mechanism, HELP or HEAD, depending on the hydrogen concentration and the material stress rate and other numerous environmental factors for practical application. So in 2009, Professor Robertson and a group of authors from the United States pointed out that it's more feasible that in metals several hydrogen embrittlement mechanisms operate simultaneously, but that one of them dominates under specific condition. Recently, we could say that in 2021, the synergistic interplay of both HELP and HEAD mechanism in different types of steels are confirmed by numerous experimental and modeling evidence. So we could summarize that the dominance of a particular, these 2 mostly accepted mechanism depends on the numerous factors. I will just list the problem. We have numerous influencing factors like a steel microstructure, source of hydrogen, hydrogen local distribution and trapping processes. Also the local hydrogen concentration and distribution and reaching of the critical hydrogen concentration. Very complex phenomena related to hydrogen dislocation interactions And of course, finally, the applied stress rate condition define which of these two mechanisms will be the dominant in particular case, and also change between these two mechanisms. So the synergistic interplay according to Hell plus heat model was recently confirmed in various type of steels you can see here, but also in a nickel and nickel-based alloy, also in iron, and more recently in aluminum alloy. So now I will talk about the difference between these two models for the synergistic action of help and heat mechanism, help mediated ecohesion model and help plus heat model. Here you can see a short historical overview. The first mechanism which was proposed was help mediated heat model by Martin Agao and the group under the Professor Robertson and Professor Sopronis from the United States. And in 2014, there are several papers related to help plus heat model. Our paper published in 2014 and also in 2015, and a review paper in 2016. And we have here numerous up to today papers which confirmed the synergistic action of help and heat mechanism in steels, but also in other materials. So here is the definition from 2014, which we further developed in 2015, 16, and 19. Help plus heat model, the synergistic effect of some or multiple plasticity-mediated hydrogen brittlement mechanisms, help or others, together with the heat mechanism, are responsible for hydrogen brittlement in steels, but one of them predominates under specific conditions. So you can see here the difference between help-mediated ecohesion model, which stated that the major mechanism always active is a help mechanism, and that an initial activity of help is always a prerequisite for the eventual activation of the heat model. So that's a help-mediated ecohesion model, while contrary, help plus heat model indicate that almost simultaneously these two hydrogen brittlement mechanisms are operative. Some of plasticity-mediated mechanism, most probably help, but also AIDI or HESIV, together with the heat model, but one of them predominates under the specific condition. That is the most important distinction between these two models for synergistic action. So when we talk about structure integrity model, these 2 points are extremely important. Most of the research of the mechanisms of hydrogen damage and brittlement was based on the previous uniform enrichment of metallic materials with hydrogen throughout the whole volume of the samples. Contrarily, during the operation, metallic materials of industrial components are usually very unevenly saturated with hydrogen due to the local corrosion processes. So the prerequisite for the predominance of heat mechanism and activation, which leads to the hydrogen-assisted degradation of crack propagation resistance, which is the most important thing for the practical preventive maintenance aspects, is reaching of the critical hydrogen concentration. Upon the reaching of critical hydrogen concentration, we have a sharp transition from the help dominance at the lower hydrogen concentration to heat dominance, and also a very sharp drop of some of micro and nanomechanical properties. The most affected properties are ductility, plasticity, and also crack propagation resistance, which we investigate as a crack propagation component of impact strength during the Shapi testing, which shows a sharp drop upon the reaching of critical hydrogen concentration. And also we have a very sharp ductile to brittle fracture transition due to the reaching of critical hydrogen concentration. So failure occurs after the degradation of micro and nanomechanical property. Also, we investigate nanoelastical modules and nano-hardness change due to activation of heat mechanism according to our help with heat model in the recent papers. So the structure integrity model was based on the real-life industrial case. We have a hydrogen damage due to high temperature hydrogen attack, and after that, uneven saturation with hydrogen during operation, which provide opportunities for viable hydrogen brittlement analysis and confirmation of help plus heat model. So we have boiler tube, we have thermal power plants. You can see here high temperature hydrogen attack. You can see here that in the vicinity of the fracture, we have a very high hydrogen concentration, which drop sharply at some distance. And we provide the connection between macromechanical properties and micromechanisms. Impact strength and hardness, we connect with the same characterization of fracture surfaces in order to reveal the critical hydrogen concentration phenomena and to provide a reliable structure integrity model for the preventive and predictive maintenance of industrial components. So you can see here the position of Sharpie specimens at some distance from the fracture, while in the case of the specimen near the fracture feature, window type fracture, we have a very high hydrogen concentration. At some distance from the fracture, we have a drop of hydrogen concentration. You can see here the micro view of hydrogen damage, hardness measurements position. We investigate typical ferritic perlitic, low carbons ST20 steel, equivalent to 1020 steel. And we use the non-standard subsized Roman tile, as you see, like geometry, Sharpie V1 notch specimen. So it's a subsized specimen in order to provide a specimen from the tube wall. Uneven saturation with hydrogen was due to the local acidic corrosion, which was the source of hydrogen, and provoked the corrosion gouging, which is mainly provoked, as you can see here, the corrosion gouging, and that gouging was mainly provoked by chlorine with a simultaneous action of electrochemical galvanic corrosion due to the copper in the presence of organic matter in the boiler tube. Just briefly, we investigate corrosion mechanism. In the corrosion pits, we investigate chemical composition of corrosion products. You can see here EDS line profile analysis. You can see here EDS points for investigation, and we can see that locally we have a very high copper and very high chlorine content, which provoked the corrosion mechanism, which was the source of hydrogenation of material during the exploitation. So we investigate the transition from ductility to, let's say, non-ductility. We use the impact strength testing. As you can see here, for some specimens at different distance from window type fracture, we have a different mean hardness of that specimen, and also we have a different hydrogen concentration. With an increase in hydrogen concentration, the mean hardness of the specimens also increase. And as you can see, for S3, for example, we have a relatively good impact strength. This is a total amount of impact strength in red color. This is a crack propagation component of impact strength in blue color, and you can also see crack initiation component in black. As we can see, in the case of S3, we have a relatively good value, while in the case of S4, we have a very sharp drop in total impact strength, but also very sharp drop in crack propagation strength, which became lower than the crack initiation strength. With a further increase of hydrogen concentration, we have an additional drop in crack propagation component of impact strength, but also the drop in total impact strength and a slight drop in a crack initiation strength. So crack propagation components are related to hydrogen assisted cracking. We have here the drop of hydrogen, the drop of crack propagation resistance of material, very sharp drop due to effects of hydrogen. So we investigated the hydrogen brittle mechanism, as you can see in the case of S4 and in the case of S3 and S4 specimen, we have a very similar fracture features. Here is the combination mix of ductile areas predominantly by microvoid coalescence due to activity of HELP mechanism and the initiation of transgranular refractured area due to activation of heat mechanism. But you can see MVC area are predominant. In the case of S4, when we have a sharp drop of mechanical properties, crack propagation resistance, and also total impact strength, we have a very similar situation, but as you can see, we have a predominance of transgranular refractured area due to dominance of heat mechanism, with the remaining area still fractured ductilely by microvoid coalescence due to activity of HELP mechanism. So in this case, we have a dominance of HELP, and in this case, we have a dominance in heat. And as you can see, we have a model and experimental confirmation of sharp drop and ductile to fracture brittle transition in still due to activation and predominance of heat mechanism. We provided in our paper in Corrosion in 2016 the structure integrity model based on this diagram where we could investigate the mechanical properties depending on the critical hydrogen concentration and to follow the drop of mechanical properties. So we can divide this diagram into 3 zones. The first one is safety zone, which means a run decision, where the mechanical property are still not affected by activation of heat mechanism. We have a help mechanism, but very slight drop of ductility and impact strength in this case. The repair area corresponds with the reaching of the critical hydrogen concentration and the sharp drop of total impact strength and crack propagation component of impact strength, which then became lower than the crack initiation components, which present the zone 3, which are connected with the immediate replace decision of the components, since the crack propagation components is lower than the crack initiation components, and failure due to hydrogen could occur very easily and very frequently. So we proposed in our review paper the summary of the unified model for synergistic interplay of hydrogen brittle mechanism and stills, where we divided 2 areas below the critical hydrogen concentration at low and medium hydrogen concentration, where we have a plasticity-mediated fracture modes, where the plasticity-mediated hydrogen brittle mechanism like HELP, ED, or HESIV are dominant, and also we have a possibility for HELP-mediated heat model at low and medium hydrogen concentration. While upon reaching the critical hydrogen concentration, we have a transition to the heat dominance, the cohesion mechanism dominance, and the cohesion control fracture modes, and also hydrogen impeded plasticity, which correspond to the actual operation of components where we have a high applied stress. Also, it is important to carefully examine the hydrogen charging method and hydrogen distribution influence on this transition from help to heat, and also stress-stress influence, which I indicate that high applied stress favors the initiation of heat mechanism. More recently, in 2021, we proposed this summary for HELP plus heat model in low carbon steel, where we pointed out that even in the case of HELP dominance at the lower critical lower concentration to the critical hydrogen concentration, we have a local incidence due to activation of heat mechanism, which didn't yet provide a sharp decline in mechanical property, as you can see on the previous slides. But we have initial heat mechanism activation in the predominant HELP mechanism activation in the form of transgranular fractured area and also intergranular cracks and specific microstructure. And during the further hydrogenation of material and reaching of the critical hydrogen concentration, as you can see, transgranularly and intergranular fractured area becomes dominant. And we have also remaining areas in gray due to HELP mechanism and microvoid coalescence area, while in the case of supersaturation, we have almost exclusively brittle fracture due to intergranular and transgranular fractured area, as shown on this picture. So in our review paper, we summarized the novel and unified HELP plus heat model, which is based on a specific microstructural mapping, as shown previously, of the dominant hydrogen brittle mechanism with implication of the fracture process and the various obtained hydrogen-assisted fracture modes. We listed here hydrogen trapping site responsible for HELP dominance, for heat dominance, and also corresponding fracture modes and transition modes, which are related to the dominance of HELP mechanism and the transition from HELP to heat dominance, and finally the heat dominance you can see here for different types of steels. Finally, conclusions of our presentation. Simultaneous action of hydrogen-enhanced decohesion and hydrogen-enhanced localized plasticity mechanisms were experimentally confirmed depending on the local concentration of hydrogen in steels, but also in other recently metals and alloys. A coexistence of HELP plus heat is characterized by a mixed quasi-cleavage-like mode of fracture with a simultaneous presence of brittle transgranular fracture of ferrite, predominantly by heat, and locally ductile fine microvoid coalescence fracture of predominantly perlitic microconstituent due to the HELP activity. Simultaneous action of both hydrogen brittle mechanism, HELP and plus heat, is responsible for the decline in steel ductility, but heat is more effective and provide a sharp transition and a sharp drop in mechanical property, including ductility, a relatively sudden manifestation of heat mechanism upon reaching a critical hydrogen concentration is followed by a sharp ductile to brittle fracture transition. And our structural integrity model developed for more than 5 years is based on the correlation of micromechanical properties to scanning electron microscopy fractography analysis of fracture surfaces in the presence of simultaneously active hydrogen embrittlement micromechanisms. Finally, the proposed structural integrity model is practical for use as a predictive maintenance in various industrial plants since it is based on the use of standard micromechanical tests. Thank you for your attention.
Thank you very much, Milos. It's a very interesting presentation. So lots of information. I got many questions, but because of the time, so I will see how many questions I will pick up for you. Okay, so anyhow, so first question. So the two mechanisms you include in your presentation can give the explanation of the behavior of hydrogen inside the metals. Okay, anyhow, so I just finished the question. For the two mechanisms, the hydrogen will remain is atom hydrogen or molecule hydrogen?
There is two possibilities. We have possibilities of nascent, which means atom hydrogen in metal, which could diffuse in the metal. But also we have possibilities of recombination of atomic hydrogen, in which case we have hydrogen-induced cracking, which is provoked by the pressure effect of hydrogen molecules in the material. So we are talking here about the atomic hydrogen effects, and the hydrogen embrittlement is one of the mechanisms of hydrogen damage. Contrary, it is important to make a clear distinction between hydrogen embrittlement provoked by atomic and diffusible hydrogen in material in comparison to the hydrogen-induced cracking, which is the consequence of hydrogen pressure in the molecular form, and it's typical for welding and some other application. And as I pointed out in this presentation, the initial damage mechanism was the third damage mechanism, hydrogen damage mechanism. In this case, it was a high temperature hydrogen attack, which is a typical high temperature hydrogen damage mechanism. So we are talking here about diffusible hydrogen, which are not recombined into the molecular hydrogen. And we still have no, but there is a possibility of combined effects of both mechanisms of hydrogen damage, in this case, hydrogen embrittlement due to atomic and hydrogen-induced cracking due to molecular pressure of hydrogen.
Okay, so let's say go to the second question. The second question is sometimes when hydrogen goes into the steel, we can observe the increase in hardness. So what percentage increase in hardness will indicate a significant hydrogen influence on the metals?
We must say that there are two possible effects. For example, if we have a relatively low hydrogen concentration in a particular microstructure, due to activity of hydrogen-enhanced localized plasticity mechanism, not only HELP, but some other mechanism, we could have a slight drop in hardness. While in the case of higher hydrogenation of material, we will have typically the hardening of material due to hydrogen embrittlement. So it is important to clearly make the distinction between softening effects of hydrogen and also hardening effect of hydrogen, because in the same material, depending on the particular condition, which means stress-strain rate condition, and also experimental conditions. For example, if we use a slow strain rate test or use a high impact strain rate tests, we could have both effects. So in the case of industrial material hydrogenation, we typically have, in the case of bolts or components of steel constructions, and in this case, boiler tubes or pipelines, typically we have a hardening of material due to hydrogen, which is related to the decrease of plasticity phenomena, as showed here on our diagram. I will show you. As you can see, we have hydrogen impeded plasticity, which means hardening of material upon reaching of higher concentration at high applied stress. But also for the same material at the lower or medium hydrogen concentration and low applied stress, we could have an opposite effect, softening due to hydrogen enhanced plasticity and plasticity mediated fracture process, which is not related to the cohesion mechanism, which is typical fracture mode, as we can see on bolts, like fully transgranular, intergranular brittle fracture. So we can have combined, as you can see here, we have something like quasi-cleavage feature, which is still undefined because it is connected with the remaining plasticity of material. As you can see, we have a microwatt coalescence area, but also we have a transgranular and initiation of intergranular area. So in this case, we could have a softening of material due to enhanced plasticity due to hydrogen.
All right. Because of time, we still have a couple of questions, and I think you can contact Milos and for the question answer sections. Anyhow, so thank you very much for your talk. It's very good.
Thank you very much.
So we continue the section, and finally we go to the last talk. Will be given by Dr. Faysal Eliyan from the University of British Columbia, and we'll talk about the corrosion control, recent progress of oil pipeline corrosion control.
Oh, good evening or good morning or good afternoon, everyone worldwide. Thank you so much, Professor Cheng, for inviting me to this conference. It is a very good chance to share with you a quick recent basic methods of controlling corrosion and dealing with corrosion in oil and gas pipelines. So the presentation now I am offering is adapted from a short paper I consolidated in it the basic methods that is followed in controlling corrosion in oil pipelines in consolidative way. Here, as you can see, when dealing with corrosion, we are dealing in a pipeline, we're dealing with complex mixtures of possible combinations of substances being delivered from one point to point and in a variety of conditions. Depending on the nature of the oil being delivered, depending on the operation conditions, and being on the corrosivity of the complex mixtures comprised of the hydrocarbons, water, and gases, becoming of different severity on the inner surfaces of the pipeline. So, in dealing with corrosion, in dealing with the control of corrosion, we keep a closer look on the content of water, of course, and also in the dissolved gases that have the ability to alter the aqueous conditions in controlling the anodic and cathodic reactions, and in driving the dissolution and the evolution of the corrosion products, mainly driven by gases, carbon dioxide, H2S, and oxygen at specific locations in the pipeline. Also, bacteria and other contaminants. So the basic things that a recent method would take care of is the pipeline cleaning, chemical treatment and inhibition, and also a proper pipeline design that would help deal with these aspects in minimizing the potential for a corrosive media to accelerate corrosion in specific critical points, especially where water or other contaminants would locally attack the inner surface of the pipeline. The prerequisites in dealing or in devising a method is first, of course, is with determining the type of the pipeline, being a transmission pipeline, distribution pipeline, upstream, downstream, etc. And also the properties, the physical or chemical properties of the oil and gas being delivered. So for the methods, they mainly 5 basic methods being followed, being applied nowadays with dealing with the gas phase contaminants, degasification, water control, dehydration or dewatering, pipe cleaning, begging, internal coating, liners, and or chemical treatments or corrosion inhibitors. These methods over the years haven't changed much, but only except with minor changes or minor strategies that would make them more efficient in controlling corrosion. For the considerations for the liquid pipeline, for controlling corrosion in it, it has to first being a field gathering pipeline with multi-phase constituents, or crude pipeline or refined product lines for gasoline, diesel, or lubricant, or LPG and NGL, etc. These are the basic considerations that first for a liquid pipeline need to be determined which category a pipeline for a corrosion control strategy being method has to be determined first. For the gas or liquid quality standards, there are standards that have to be followed. Some deviations from the controlled or operational conditions that have been already studied or have been determined could happen, so that they would change for sure the method, or should change for sure the protocol that is applied for controlling corrosion, especially during shutdowns or during some failures or unexpected failures or problems. Also for some combinations of gases, aqueous liquids, or contaminants such as chloride or bacteria in pipelines also could change the method being decided on for controlling or mitigating corrosion, and for a pipeline specific critical locations for which corrosion expectedly could be the highest or could be high. So as I said earlier, the environmental control, we consider the amounts or the concentrations of carbon dioxide, H2S, or oxygen must be, of course, limited. The constituents of water in a pipeline not being removed, also, of course, by dehydration. If B also determine the effects of the extent of damage, of the expected damage of CO2 in soft waters condensed from steam. CO2 creates corrosive conditions. We know carbonic acid, the reduced pH, these constituents drive and accelerate the cathodic reactions. Carbon dioxide increases acidity, and also it drives the formation of the carbon-based corrosion scales that would, with time, reduce corrosion at a later time, but they cause damage and accelerate the anodic reactions. In hard waters, the carbonate and bicarbonate, they also get involved in the anodic reactions in addition to the cathodic reactions. And with magnesium or calcium, they complex. They are complexing agents that could also get involved in the formation of protective scales that would reduce the anodic reactions with time. H2S produced, of course, as we knew, adsorbed hydrogen protons and adsorbed hydrogen atoms that would lead, of course, to hydrogen blistering. These are the basic constituents that drive corrosion at a high rate in the beginning, but with time, they contribute to decelerate naturally corrosion in a typical oil pipeline. degasification depends to a great extent to the operation conditions and to the operation standards. Degasification also could happen naturally with respect to temperature. The higher the temperature, the degree to which the dissolved gases could contribute in attacking the inner surfaces could be less. This is a basic thermodynamic phenomena for which the extent of dissolved gases could reach to in attacking or degrading the inner surface of a pipeline. This is accompanied with the decomposition, with the evaporation, or any unwanted reactions, or even wanted reactions at a certain point. Degasification could be substituted with with purging of inert gases, or the addition of reductants or scavengers. There are some techniques that could involve the direct degasification, like membrane degasification, that would remain the most comprehensive method in removing unwanted corrosive gases in critical systems. Redissolution of removed gases is eliminated and the pure base liquid remains. So for the membrane degasification as a comprehensive method, it requires a dedicated machinery, and it maybe is more suitable for smaller scale piping systems, and it could be also expensive and could also require regular maintenance as a machine dedicated for degasification or for removing gases from running multi-phase fluid. Water control, water cuts could be very high, could be high in multi-phase flows, and especially in the initial stages of the piping system, in the gathering lines, and could be limited in stages in the product lines. And crudes in general could contain as much as 2% of water, but they to a great extent influence the mechanism, the likelihood of internal corrosion, and also could change the entrainment regimes, the flow regimes, and in the end dictate the mitigation strategies. Removal of water from pipelines is necessary, and can be but is necessary, of course, but the complete removal of water is impractical. In some gaseous systems, for example, water vapor can be removed by alcoholic components, like by triethylene glycol or diethylene glycol. Glycol has excellent hygroscopic properties, and due to it has high stability in high temperature and low pressure environments, and also can be, as you can see here, can be regenerated by cyclic heating, as you can see here in the as you can see here in a schematic for a gas processing plant here. Water vapor in aqueous systems absorbs to the surface at low humidity, but causes, like, trivial corrosion rates, as electrochemical reactions couldn't be supported by the vapor alone. And that is related to the dew points. With glycol dehydration, the dew point decreases as water vapor is removed from the gas at interface with local glycol water solutions. You can see here in this figure the vapor dew points over aqueous dipropylene glycol solutions. And if for this graph, for example, if some graphs are not available, the atmosphere or the equilibrium amounts in relation to the glycol solutions and atmospheric pressure some equations can be used for that. For settled water in pipeline systems, like as you can see here in this figure, drips are used to remove excess accumulated liquid with arrangement shown as you can see. There are many designs for the drips, but they are produced and used without specific standards yet, and they are high, but they are at the high level of frequent practices in the field, and they are beneficial to use in variety of conditions. There are also another method for dewatering, often used in conjunction with drips involving running cleaning bags. These are familiar components that have been used for many years, and they witnessed some modifications in adaptation with the conditions, in achieving higher efficiency, higher better piping practices, pipeline intervention gadgets or BIGs used for maintenance and inspections operations. They initially were intended to be used only for cleaning purposes. Now quality control, pipeline ovality, they are now being used for quality control, for controlling or measuring the ovality, and achieving or measuring any problems or inspection purposes. So for example, for the cleaning or dewatering, bags are manufactured from polyethylene foam, as you can see here in the figure. They are compressible, flexible, and lightweight. For these bags, they are more robust, and they have metal body with sealing discs as barriers between high pressure and at the rear part, and low pressure at the front part. The pressure difference propels the bag with the pipeline in stream without disrupting operation. Brushes or scrapes could be installed between the seals to remove hard deposits. For the solid cast bags, they are made from urethane, have similar functionality, known to combine and have flexibility and ease of handling of foam bags, and they have good durability and sealing capabilities. These are the basic types of bags that are in recent use in pipes. They haven't witnessed a great modification or great improvement, but they still are the best choice for cleaning and inspection. For internal coatings and liners, they in fact are very good in mitigating corrosion, and they prevent precipitation of corrosion products, and they improve flow efficiency, and they achieve a very good cost. They have good cost capabilities, cost effective. They are a cost effective method in reducing in driving and pushing the flow and reducing the maintenance costs. They cannot substitute inhibitors, and they are prone to defects and despondence, and they are also prone to hydrogen-based attacks. They also often make inspection with bags or smart bags challenging. So they, in some sense, improve flow efficiency and reduce costs of maintenance, but they cannot prevent corrosion, or they could be a source of other problems. For the chemical treatments and inhibitors.
1 minute, please. Can you just speed
sure.
up, please? Yeah,
absolutely. For the inhibitors, they have to have compatibility. They have to have temperature stability. They have good partitioning behavior, and they must have performance testing results. Mechanistically, inhibitors reduce corrosion rates and also they have they reach and absorb on the metal surface, and they increase the resistance of corrosion products. There are a variety of types of inhibitors, and they, and according to the type, according to they can control a variety of corrosion reactions in a pipeline. And the criteria for ideal corrosion behavior or corrosion inhibitor, they should be compatible with other chemicals and with other materials. They should have adequate deliverability. They must have also stable absorption and persistence. There have been a lot of studies that link the operation conditions to the performance of the inhibitor, as you can see here, with respect to the temperature or the concentration. And the basic aspect in relation to the function of the inhibitors, which have been developed recently, is in regard to the solubility and partitioning. Also, with the microbiologically influenced corrosion, you can see here that they are still a source of a variety of problems in the pipelines. And for that, biocides have been developed for that. And they are a variety of types and categories that have been devised to control the microbiological influence corrosion. And the biocide selection is not as easy as selecting an inhibitor. The selection must be based on tests and evaluations from the field. Simulating corrosion conditions exactly from a pipeline is difficult, is not as easy as it would be for inhibitors. So the role of the field and the experience from the field is very important for selecting a biocide, for controlling the microbiologically influenced corrosion. So in summary, I can say that the basic aspects that for any new or old method that should be devised for controlling corrosion must focus on the gas phase contaminants and degasification, must be based on water control and dehydration or dewatering, must also be based on regular cleaning and bagging for both cleaning and integrity measurements, must also be based on the use on the effective and cost-effective use of internal coating or liners, and also, of course, in the end, the suitable laboratory based and field-based suitable selection of chemical treatments and inhibitors. Thank you very much indeed.
All right, thank you very much. Because it's behind the schedule, but I still want to give you a very quick question. Can we use batch picking to mitigate the risk of top of the line corrosion?
In fact, no, it can't be used for this. In fact, the bagging have been most reliably recently used for measuring the defects, measuring problems, inspecting, but not for a complete or reliable prevention of corrosion in pipelines. And it's similar to other methods that have been used for controlling or mitigating corrosion only at the beginning, let's per se, or at the end per se of the pipeline to measure the effectiveness of the method that have been used.
All right, okay, thank you. We still have a couple questions, but because of the time, I apologize, cannot give all the questions to you, but I think it's probably someone will contact you for the questions. So that concludes our section, and thank you very much for everybody to attend the conference and the section. So that's a very good and section and very good talks. So next, back time to the organizer for any potential announcement. Thank you.
Thank you to Dr. Cheng for chairing this session and for the speakers. Thank you to all our attendees. The second day of the conference is obviously tomorrow. It will be starting at 8:45 Central European time. So we look forward to seeing you then. And I wish everyone a nice evening or afternoon or morning, wherever you are. Bye-bye, everyone. See you tomorrow.